Okay, continuing with the 11.3, this is part 2. We'll calculate the area of a regular polygon, but we need to review what a regular polygon is. A regular polygon could have any number of sides, 3, 4, 5. It has to be a whole number, and it has to be at least 3. But a regular polygon meets 2 requirements. All the sides are congruent, and then all the angles are congruent as well. So an example of a regular polygon would be an equilateral triangle. All the sides are congruent and all the angles would be congruent, or each of the angles would be 60 degrees. Another example of a regular polygon is a square. All the sides are congruent and then all the angles are 90 degrees. But let's take a look at one specific regular polygon. I'm going to look at a regular pentagon. So a pentagon has 5 sides. All the sides would be congruent. All the angles would be congruent as well. If you want to find the measure of each of the interior angles, like I just listed, even though they're all congruent, we can find the measure of the interior angles. If you remember the formula, n minus 2 times 180, that's the sum of the interior angles. So in this case, n is 5, 5 minus 2 is 3, and then 3 times 180, the sum of the interior angles would be 540 degrees. Then to find the measure of each interior angle, in this case there's 5 interior angles, you could divide 540 by 5 and then get 108 for the measure of each of the interior angles. You could do that for really any regular polygon. But let's just say I inscribe the polygon inside of a circle. Then we could take a look at the parts of a regular polygon. So the center of the circle would be the center of the regular polygon as well. And then from the center to a vertex, since each of the vertices, if the polygon is inscribed inside of a circle, the vertices would be on the circle. This is the radius. So from the center to a point on the circle, which would actually be to a vertex in the regular polygon. If I inscribed a, say, hexagon, decagon, whatever, that would be the radius. But then here's another part, an important part of a regular polygon. If you go from the center perpendicular to one of the sides, that's what's called the apothem. Or once we put that into a formula, the abbreviation would be A. But to define the apothem, it's from the center of a regular polygon perpendicular to one of the sides. Because in order to calculate the area of any regular polygon, this would work for the regular pentagon, it would work for an equilateral triangle, it would work for a square, regular hexagon, whatever, but it has to be a regular polygon. The formula is as follows. The area is 1/2 the perimeter of the polygon. So if you know a side length, then you know the perimeter because all the side lengths would be congruent. It would just be a side length multiplied by the number of sides, and then multiplied by the apothem. Or you could also write the formula like this. The perimeter, like I said, is the number of sides, n, times a side length, s, so that's a perimeter, just n times s, and then times a. Maybe you'll see the formula written in a slightly different order. Instead of 1/2 perimeter times apothem, it'd be 1/2 apothem times perimeter, but it's the same thing. You could write it in any order, 1/2 perimeter times apothem, or 1/2 apothem times perimeter. And then we're going to apply that on some of the examples.